Okay, so now let's go ahead and move on to finding the domain of rational functions. And if you kind of remember from the warm-up, the writing the domain is not always easy, just as writing down all the numbers that are in the domain, kind of like, if you're given a table or points or even radical functions we just found what values made the domain true. With rational functions, it's usually like one point or a couple points that are undefined. Besides that, everything else is defined for the function. So when we're finding the domain of rational functions, what we're going to want to do is find the discontinuities, find the values that are undefined of the function, find the values that are not defined in the domain of the function, that are not on the graph. And if you want to, I provided a link to the graphs for each one of these, so you can kind of like go ahead and check your answers. For time purposes, I'm just going to leave that. I'm going to leave that off on the video because I think you can go ahead and check those, on your own and see for yourself. But I'm just going to show you the algebraic way, and then if you want to try it on your own, then you can just go to this link and see how the graphs relate to the domains that we found. So the main important thing to remember is we cannot divide by 0. So when we're doing rational functions, the main important thing we want to do is find the values that make the denominator 0. And again, notice I said find the values that make the denominator equal to 0. We actually don't really care what's in the numerator. Now we do for certain different types of problems, but as far as identifying the domain, the numerator is not going to affect the domain when we're dealing with the rational function unless it's like a radical or some other type of function. But if it's just like a polynomial or it's a continuous function with no discontinuities, we're not going to worry about it. So like for instance, in this example, all these numerators here do not have any discontinuities. Like there's no radicals or logarithms or something crazy. So since we have a continuous function in the numerator, we're just going to be focused on when the denominator is equal to 0. So the main thing that really I'm going to do for each of these problems, the first step is set the denominator equal to 0. So x minus 1 is equal to 0. I want to find the values of x that make the denominator equal to 0. So I go ahead and solve by adding a 1 to both sides. I get x equals 1. And again, when x is equal to 1, the denominator is equal to 0. So when we're thinking about the domain is true for all values except for 1. So we could say like the domain is for all values except x cannot equal 1. Now x does equal 1 is what we call our discontinuity. And we'll talk more about discontinuities here at the end of the video, or at the end of this day. So let's just go and think about the domain. So again, like if we're going to write out a linear graph of this, at x equals 1, the domain is undefined. So I'm going to use a open point to represent that at 1 it's undefined. But for all other values, there's nothing wrong. We can plug in any other number we want to for x. We just can't plug in 1 because when we plug in 1, that makes the denominator equal to 0. So how could I write the domain for this in interval notation? I don't know why I'm using red again. Well, the values can go all the way to negative infinity. And then they can go all the way to this value 1, but they can't equal 1. So that's why we use the open bracket. So it's 1 with parentheses is basically saying it's going all the way close up to 1, but not equaling 1. And then if I jump over that open value, I can again start back at 1 and then continue with all values going all the way to infinity. That is what's going to be defined for the function. The only value that is not defined for the function is when x equals 1 because there's a discontinuity there. And we remember we looked at the warm-up, it looked like it was an asymptote that occurred there. It's not always going to be asymptotes, and I'll even like go through a little bit extras on these. But in this case, it would be an asymptote if you want to verify in the graphing. All right, so in this case here, now we have a product of two expressions. So again, just set them equal to 0. So x minus 2 times x plus 7 equals 0. Now in this case, since I have the product of two expressions equal to 0, I can apply the 0 product property. So I can just say x minus 2 equals 0 and x plus 7 equals 0. And then I can just solve for x here. So I can have x equals 2. Or x is equal to negative 7. All right, so let's just verify again. These are the values that make the denominator 0. If I plug 2 in, 2 minus 2 is 0. 0 times anything is going to be 0. Negative 7, plug negative 7 in for x here. Negative 7 plus 7 is 0. 0 times negative or negative 9 or really anything is going to be 0. So these are the two values that are undefined for my function. So again, kind of going back to that number line case, I have negative 7 is undefined. open circle. Positive 2, open circle. Every other number is perfectly fine. Doesn't matter what any real number I can plug into is going to be good. So my graph is going to look something like this. So to write this, now you can see we kind of have like 3 versions of our domain. We can write an interval for this section, an interval between this section, and an interval for this section. So the way that it would look would be negative infinity to -7. Again, -7 is undefined, so therefore we're going to use a parenthesis. And then we're going to go from -7 for space purposes. I'm not going to use the union symbols. Again, union is just connecting those domains. Then I'm going to go from -7 to 2, and then I'm going to go from 2 to infinity. And again, it's really important that you understand the parentheses and not the brackets. Brackets would mean that 2 is included, and 2 cannot be, or 2, oops, did I forget? What did I do here? -7, yeah. That 2 or -7 is included, which it's not, because then it'd make the denominator 0, so that's not good. All right, so let's go and look at the next example. Now, I did kind of get into, hey, just, set the denominator equal to 0, don't worry about the numerator, but that's not really what I want you to take away, because you do have to be cognizant of what's in the numerator or aware of what's in the numerator, because once we get into this later as far as identifying discontinuities, the numerator, while it doesn't, as long as it's a continuous function, doesn't affect the numerator, it will affect the type of discontinuities we have. And in this example, I'll explain why. So let's just factor both of these. Now, in these first 2 examples, there's nothing you could do to simplify it, so I didn't even talk about it. In these next 2 examples, we can do some simplifying. So what I'm going to do is I'm just going to simplify the numerator and the denominator and kind of see what comes up. So in this case, I get x minus 2 times x plus 2. And then over here, I can factor out an x, and I'm left with an x plus 2. All right, now, while this divides out, that's great. That's going to help us with our whole, or identifying our whole, but that's not going to remove the discontinuity, because this is still your denominator. That first step that I told you to do still remains the same. Take your denominator and set it equal to 0. Now, you could even take the factor form of that, which would have been faster, but just want to help you guys out with that. As far as you factored out, now you can apply the 0 product property, x equals 0 and x plus 2 equals 0. Therefore, x is equal to -2. So therefore, again, if we look at a number line, here, we have -2 and we have 0. And those are the only values that are undefined. Every other term works. So, everything else in my number line is good. So the domain is going to look very similar to that. I can basically go from -infinity to, -infinity to -2. Union, -2 to 0. Union, 0 to infinity. In this case, I'm using the union symbols because I usually like to prefer to use the union symbols for each time. Now, kind of going back up to here, I'm going to talk about this next, so I don't really want to go there, but you guys can see that this divides out, right? And that is what we call a removable discontinuity. It's removable because you can technically remove the x plus 2's from each other because they really divide out to 1. So that's a removable discontinuity, which when you look at the graph, you will not see an asymptote there. It's actually a hole. So I thought I'd mention it just in case you're looking at the graphing portion of this. All right, let's move on to the next one. I think I can factor this over to the right-hand side. On the top, I have x squared minus 1, so that becomes x minus 1 times x plus 1. Again, that's a difference of 2 squares. In the denominator, what 2 numbers multiply to give you 3, add to give you -4. That's going to be x minus 1 times x minus 3. Okay, and then again, you can see that again we have this removable portion. But again, be careful. Don't simplify it and then say, oh, the only discontinuity is at x equals -3, because that is not true. I'm going to set the factored form here just to kind of save myself a little bit of time. So this would be x minus 1 times x minus 3 equal to 0. So again, what I did is I just took this and factored it down to that form, setting equal to 0. So you could have just set this equal to 0 and then factored it either way. Then I set them both equal to 0 by the 0 product property, which I've already shown, so I'll skip that step. So therefore, I have x equals 1 and x equals 3. And again, guys, this is like the same thing. don't need to draw a number line to do this, but I just like to kind of have a visual representation here. So you can see that everything is in the domain except for the numbers 1 and 3. Because when you plug in 1 and 3, it doesn't matter if you plug them into 1 and 1 here or 3 and 3 here, or if you plug it into that form. Either way, you're going to get 0 in the denominator. So my domain in this case is going to be from negative infinity to negative 1. Again, negative 1 is not included. Negative 1 to 3. And then union 3 to infinity. Okay, so basically when you're dealing with radical or with rational functions, it's really kind of the same. The only time we start getting into variations is once we start mixing them together or mixing in some other equations. So that's what I'm going to do next is I'm going to mix together in some rational and radical functions in together so we can start seeing how the domain starts to get a little more complicated.